Good evening, everyone, and welcome to the BS and Beer Show. BS stands for Building Science.
Perfect timing.
Tonight's topic is the science of concrete. My name is Ben Bogey. I'm a project manager in Connecticut, and this evening I'm drinking a sour ale from City Steam Brewing here in Connecticut. BS and Beer is an independent grassroots movement to share building science knowledge through local meetup groups and this, our Zoom show. The brew crew and our guests volunteer our time each week to bring you what we hope is a fun and informative discussion. We'd like to thank Green Building Advisor and Fine Home Building for their steadfast support of us and putting this thing together on a weekly basis. And with that, over to Kylie for some announcements.
Yep, thanks, Ben. Nice to see you all. I'm Kylie Jacques. I'm the senior editor at Green Building Advisor. I am back to the weather is warming up, so I am back to my Topo Chico with a twist of lime. It's refreshing. Same old stuff. When you engage with the chat box at the bottom of your screen, just make sure you click all panelists and attendees so everybody can see what you're saying. Fine Home Building sends out Zoom reminders about the show each week, and if you want to get those or as well as additional information, join our mailing list at the bsandbeershow.com. The video recording of tonight's show will be available at Green Building Advisor on Sunday morning when I post the blog that gives a recap of the show, as well as a glimpse into next week's show. And past shows can be found on YouTube. An audio-only version, if that's how you prefer to take your media, is available on Spotify and Apple Podcasts. But as Emily always mentions, the fact that we have some really great presentations typically, so you may want to be able to see the show as well. I'm going to share some links to events, recommendations, and a recent GBA article. In fact, it was just a couple days ago relating to this very topic that we're discussing tonight. So I'd like to share that with folks. I hope to mention it. And with that, I think it's Travis for announcements.
Hello. I'm Travis Brungard. I'm in Prairie Village, Kansas, just outside of Kansas City. I'm going to drink a Boulevard Chill Vibes as soon as I have finished driving home, but not while driving home. Even I have limits to my drinking commitments. I wanted to take a moment to introduce our guests. Tonight, I'm thrilled to have my good friend Trevor joining us. Trevor Acorn is an engineer at Walter P. Moore and has been in the building industry since 2005. As a timber expert, Trevor often takes on higher education and commercial office projects. His work includes the University of District Development, North Kansas City High School Addition, the Altria headquarters expansion, and the Johnson County Medical Examiner facility. Trevor is kind of a badass and also a rock climber, but I'm sure that other people know other cool things about you, Trevor. Would you like to share what I have left out?
Oh my gosh, thank you, Travis. Well, for those who don't know, I've been a longtime friends with Travis, and we live not too far away from each other. I'm in Kansas City, Missouri. Travis actually did a lot of the renovation on my home years back when we first moved into Hyde Park. Yeah, I mean, I don't know. I'm actually not drinking anything right now because I'm about to go climbing right after this, and I think it's probably better to not do that. But yeah, I'm consulting structural engineer. I work on little tiny projects and super giant projects, kind of everything. I love what I do. Done a lot of concrete over the years, and in recent years I've done a lot more timber, but those are my two favorite materials of all. So happy to be here.
We're glad to have you back, Trevor, and it's really nice that you're not still mad at me about all the work I did at your house. I've gotten so much better since then. I feel like I should come back and fix some things.
I don't know about that, Travis. You're doing great work. I really
Stay away.
I love what you do.
You're very kind. Our next guest is Helen Watts. She's an engineer with Criterium Engineers. She has over 30 years of industrial, bridge, commercial, marine, and residential hands-on professional engineering experience. Her career includes engineering positions in construction, facilities management, and structural design. She also ran her own structural engineering consulting business for more than 12 years. Helen, it's a pleasure to meet you. How are you today? What are you drinking?
Well, I've got, see if I can put it so you can see it, Ricker Hill Maniac, and it's Macintosh cider.
Nice.
Lovely. Did I leave anything important out of the introduction?
You fit right in here on the East Coast.
That isn't what I gave Mike Maines to go and say. What I told him to say was that my largest concrete placement was one rectangular chunk, 400 cubic yards. It was a roll grinder
Okay.
foundation installed with ice in 1980. And the view behind me is Scott Winslow Recycled Fiber Facility. We built that, and 2 years later, they closed the paper mill. That was the one with the pump truck's pump valve broke in the middle of a 300-yard pour.
Ooh.
Helen, did you just say that you used ice on that mass concrete pour?
Yeah.
Maybe you and
And-
I should talk about that after the fact.
And
This
one
is
of the
interesting.
rod busters got right up there to the concrete truck showing up, and he dived in and took out this bird's nest that had been made in the rebar cage. He just couldn't take it anymore and rescued this poor little bird nest. I'm also the author of the graphic handbook of the Pretty Good House. Maybe we can see this, maybe we can't. And the so well-named volume 2. My daughter's upstairs editing the 3rd version of these 2 books. So yeah.
Where can people get those, Helen?
Hang on a second, that's my phone. Power off. Go away. Wow. All right, what was the question?
Where can people get the visual handbook?
It's on Etsy, and they're 99-cent downloads, and it was just the best way to get it in people's hands. It's not a coloring book because grown men won't buy coloring books, but
That's not
it's
true.
something for it's something for a contractor to say, here's what I'm talking about when I talk about the Pretty Good House. So, it's 24 pages of content in each of those 2. And what I'm doing is I'm taking the 2 books and I'm turning them into one updated book. So the first one's 2013 published. The second one was 2017 published, and I swore I was never going to do this ever again before I did volume 2. Here I am. The Pretty Good House.
Your tenacity is admirable.
The Pretty Good House 2021. It was going to be the Pretty Good House 2020, but I was told nobody would buy anything that said 2020. So yeah, so it gave me another year. I'm just good with that. Yeah.
That's great. Are you working on that with Mike or
He
independent?
told me to get my book done so that he could advertise my book with his book.
His book. Oh, okay, great.
So he's doing the hardcover, and I guess you guys are paying them to write.
They're doing a
What
full
is this
book, yeah.
payment of which you speak?
Well, that's fantastic. We're grateful to have you, and we really appreciate your work on the Pretty Good House. That's such a wonderful thing to be part of.
Yep.
I'm also privileged to introduce our 3rd guest, Chris Genest. Christopher Genest. Do you prefer Chris or
Chris
Chris?
is great. Yeah, nice and formal. Chris is fine.
Perfect. Well, Chris, it's a pleasure to meet you. I'm excited to have you on. Chris is president of Comfort Block and general manager of Genest Concrete Works, a 94-year-old family business that manufactures concrete products, including blocks, paving stones, and retaining wall systems. Chris designed and developed the Comfort Block masonry system and is certified as a concrete products lab technician. Chris, what are you drinking tonight? What do you got going, man?
I got a little leftover Woodford Reserve from
classy.
Well, we had a Kentucky Derby party, right? So a couple weekends ago, and it's left over. So I'm just sipping on that a little bit. I didn't have any beer in the house. I don't know. So that's
You know what?
having.
That's some
Decent
high
substitute.
end-
Yeah, right.
But I've had a lot of beer in the past, so I'm okay with that.
Your credibility is intact. Did I leave anything important out of your introduction there? I felt like it was short and sweet, but I feel like we don't know about your hobbies. What else is going on in your world, man?
Oh, I don't know. I tend to be I tend to keep building things. I don't know why, but I'm addicted to building things. I like designing various stuff. I don't know. In the past, I played a lot of hockey. I'd like to do that when I can, but I don't know. Family's happening, so that this is what I do.
Very familiar with that. Well,
Yeah.
we're grateful to have you. I know that someone's going to kick off a presentation. I'm actually going to turn off my video so I'm not super distracting. I have a little drive ahead of me. But before I do that, I wanted to give a quick tip of the hat to Scott Dion, who sent me this fine Timber HP hat. I am really grateful to have you guys on. I have a lot to learn from you. This is one of my weaknesses in building. I am not a concrete expert. So I'll hand it over. Who's presenting first?
Great question.
Trevor.
Am I? Okay. Thanks for reminding me, Helen.
Trevor, you've been nominated.
Yeah, no problem. I put together a whole ton of slides, and I'm gonna run through them with the idea that we can ask questions and have Helen and Christopher kind of jump in towards the end. So let me do that. And if you hear my kids screaming in the background, I apologize in advance. All right. Does everybody see my whole screen, or do you see the video of other people's faces?
Just your whole screen.
Your
Okay,
whole
good.
screen, and I see like little people on the right here.
Let me try.
Yeah, that's
this.
fine.
This
Yeah,
is good.
yeah, that's good.
All right, so let's talk about concrete. What is it? It's not just cement. It's a binder, which is cement and lots of other possible things like lime, fly ash, slag. We also use rocks, aggregate, sand, and larger rock. It has some amount of air. It's water, of course. And then a whole bunch of other stuff that we call admixtures, which are different things that that trick the concrete into behaving the way we want it to behave. Concrete was created a long time ago. I always thought it was in Rome, but you know, I think there's an argument to be made that in Egypt and China, they used lime-based mortars. And even before that, apparently these traders in Syria and Jordan used it. But it kind of fell out of favor, and the trick to making it was lost after Rome. And it wasn't until the late 1700s, 1800s that these two guys, Sweden and Aspen, kind of recreated it. And so Joseph in 1824, he created the first modern day Portland cement from chalk and clay. And shortly after that, Joseph Monnier, who made clay pots, interestingly, was interested in making pots out of concrete, but they kept breaking on him. So he added steel bars, steel hoops to prevent them from breaking. And that was the first reinforced concrete in the late 1800s. So again, the binders, back to concrete. Portland cement is the most common and most widely used and known, but we also mix in fly ash, which is a byproduct from power plants, and slag, which is a byproduct from steel manufacturing, and silica fume also is used as a cementitious product in addition to Portland. We make Portland by dumping it into these giant kilns where we apply huge amounts of heat. And by it, I mean limestone and clay. And in that process, the clay and the limestone turn into silicates, primarily these dicalcium and tricalcium silicates. And that clinker that results, I think I have a picture of it in here. Yeah, it's there on the in the middle right. That clinker is ground up, and that's what we get Portland cement out of. And so here's the most nerdy part of the whole presentation is all this chemistry, which I hate chemistry, but what you're seeing is the chemical reaction. So like the big ingredients, the big bulk of cement is these tricalcium and dicalcium silicates that make up 75% or 90% of the concrete or of the cement. You mix that with water and you get the important thing here. It's a COS, and this calcium silicate hydrate. That is the core structure that binds the aggregates together and really makes concrete. So this is the most important chemical part of concrete. There's a bunch of other stuff in the cement, and it's a really complicated chemical reaction that's going on. But the most important thing again are these CSH molecules. Here you kind of see what they look like. So in the early stages of concrete, you get that calcium hydroxide and this tringite, I think is how you pronounce that. But shortly after that, these calcium silicate hydrate or CSH molecules start to form. And so there's a picture of the cement grain, and then oh wait, hold on 1 second, I'm sorry. I've got kids that just got home from school. Yeah, so we get CSH crystals that form from the cement grains, and that's really the core of the structure of concrete. I think it's important to note, though, that concrete takes a lot of heat. I should say cement takes a lot of heat to form. So all that heat creates a lot of CO2, obviously. The chemical reaction itself also creates a lot of CO2. And pound for pound, cement is just about 1 pound of CO2 creation for every 1 pound of cement. So it's pretty carbon heavy. This is a popular image that is shared around. It kind of indicates that concrete is a relatively low embodied carbon. And that's true based on weight, but I want to point out here that it's not really true because it's a heavy material, right? So it's low carbon maybe per pound, but it's a lot of pounds. So concrete, we bind it together with Portland cement, fly ash, slag, and silica fume, like we said. And then the aggregates that we use are typically divided into 2 different types, coarse aggregate and fine aggregate. Coarse aggregate are aggregates that are retained in a 3/8 inch sieve, so anything 3/8 inch diameter and larger. And fine aggregates are really just everything that passes that sieve. Aggregates are important for a few different reasons. The durability of the concrete is in large part a function of the aggregates that are used. And then the shape and the size of the aggregates and the strength of them impact the overall strength of the concrete and its overall characteristics such as pumpability. Air is another big part of concrete. It naturally has 1 to 4% air entrapped in it. That air is kind of useless. We will add essentially a soap to concrete, which creates the little air bubbles that you see on the right. And that's what entrained air is in a concrete mix. And anytime we have freeze thaw, it's important to add this entrained air. It creates a path for the water that's naturally in concrete to expand into and prevent it from causing the concrete to crack and to basically explode on you. The last thing here is admixtures. There's like a witch's brew of different options that we can add to concrete to make it do all sorts of different things. The most common ones are like the air entrainment that I mentioned. We also do water reducing admixtures, which I'm going to talk about water and concrete in a minute. We'll use accelerators to make it set quicker, or retarders to delay the set. We might add shrinkage reducing admixtures to keep cracks at bay. We might use different like crystalline forming waterproofing admixtures in like a foundation wall to keep water from passing through the wall. Or often on like slab on grade or slab on metal deck, we might use the moisture vapor reducing admixture anytime we're gluing something down or we're worried about moisture coming out of the slab and affecting our finishes. And we might also use the nano silica. This is a more recent admixture to help with the finishing of the concrete or the durability of it. So when we specify concrete, there's a handful of things that we keep in mind. I think Helen might talk about this a bit more later, but most engineers use a performance-based specification where we leave it up to the ready mix supplier to kind of tune the mix to the project requirements. And that's more of a modern development. Historically, concrete was a prescribed mix, and I'll talk about that in the future slide. In the past, the engineer would specify exactly how much cement, exactly how much rock, everything that would go into the mix. We rarely do that anymore. But another thing we consider in our specs are the size of the aggregates. We'll use larger aggregates on foundations and areas where you have lower cover, or you want to get maybe lower cost also. We might also change when we require the strength of the concrete from 28 days, which is very common. We might use 56 or 84 days as a way to lower the cement and lower the cost of the concrete. We might also specify a maximum amount of cement if we have sustainability goals. That proportion mix that I was talking about, this is like a standard one. Historically, you might see a 1-3-3 mix, which corresponded to about a 3,000 PSI concrete. And it would be 1 part cement, 1 part stone, 1 part sand. And that mix would have been about 517 pounds of cement in it. The same mix, depending on where you are in the country today, with different admixtures and varying the rock, the size of the aggregates, etc., could be 3,000 PSI strength, but have only 250 pounds per yard, or around that. So we're making a lot of progress in concrete, thankfully. Right sizing members, I think, is important. And I like this quote I heard from another engineer: strength is essential, but otherwise unimportant. A lot of people are really caught up in the strength of the concrete that they deliver and provide. And honestly, as a structural engineer, I don't care a whole lot about the strength. I care a whole lot more about the durability, which in part is a function of strength, depending on what we're talking about. But I care about durability and serviceability, the life of the concrete and how will it perform over time. And so durability is a function of a lot of things. And there's a lot of things that we think about, I should say, with durability. The quality of the finishing and the curing has a huge impact on it. The exposure to freezing and thawing is very important. The aggregates that we use can be very important. We don't want to create like an alkali aggregate reaction, alkali silica reaction in concrete. And we have to consider things like sulfate attack and chemical attacks and corrosion of the rebar. There's a great guide from ACI on this, and I recommend it to all my structural engineers because the big takeaway with durability, I think, is permeability. And essentially, the lower permeable concrete, the better and more durable concrete that you're going to create. And there's a lot of ways to get to low permeability. I'm going to talk about 3 of them here, but that's the thing to keep in mind, I think, for building structures and designing concrete structures that'll last for the long haul. A few things here. So if we use a well-graded mix, so if we use, instead of just large rocks and small sand, we can pack the concrete tighter by using a well-graded mix. We can also use a lower water cement ratio. So we might want to use a water reducer, for example, to get some of the water out of there. The graph on the bottom right kind of shows the importance of that. For 4 different mixes at the same water to cement ratio, for 4 different mixes, as the water cement ratio goes down, the porosity also goes down. So water, essentially what happens is when we mix water into the mix and we have more free water than the cement is required for hydration, that water has to get out of the concrete. And in getting out of the concrete as it dries and cures, it creates the little paths that you see in the image in the top right. And those are now paths for chemicals, for water, for air to enter the concrete and cause issues in the future. So for good reason, structural engineers are worried about water. And this is why, in large part, is because it creates higher permeable concrete. So we can plug up those holes. We can use slag and fly ash to have a slower set and hold that water in longer and create less porosity. We can use crystalline waterproofing, which plugs them up. We can use these moisture vapor reducing admixtures or nano silica admixtures. And those are all ways to plug the holes and increase the durability of your concrete. So I'm coming towards the end. These are just examples of how we specify concrete at Walter P. Moore. We use a mix. We specify a different mix, or I'm sorry, we use this matrix and we specify a different mix for each application. You know, this might not make sense for a smaller residential project, but on large commercial projects, this is how we handle it. We do a few different things here. We say when, not only what the strength of concrete is, but the strength of concrete at what time period. So you can see the bottom left, we have a lot of footings and foundations are at 56 days. That's our company standard. We have durability requirements such as the air content, and I think we've got, yeah, missing some other stuff here, but you know, fly ash, slag. If we have sustainability goals, we might even show a maximum cement content, and then our maximum aggregate size. These are just some example mixes from Kansas City, local supplier. I can swing back by these if anyone is interested in talking about it. This is just an example in Marin County, California. They're actually requiring that every concrete mix meet an embodied carbon limit. And I think we might see more of this in the future. And my last two slides are just comparison between a basement. This standard basement has 10 tons of carbon. If we switched it to a slab foundation, we would reduce that to 4.5 tons for the same footprint. And that's all I had, guys. So let me jump out of here. Is everybody still with me?
Yeah.
Yep.
Great.
Thanks, Trevor. That was great.
Yeah,
nice
I flew
presentation.
through it, and I'm expecting there'll be questions, and maybe we can go back to address any of that. But
We are certainly tabulating questions on the behind the scenes here.
okay.
But I don't know if Chris or Helen, you guys want to take some time to go forward with anything that you guys have before we dive headlong into questions.
I have a presentation. Chris, you've got a couple of slides.
Just a couple. I mean, you're welcome to do a presentation if you
Mike,
want.
why don't you run mine?
Yeah.
There we go. Concrete.
Oh,
It's
nice.
not for lightweights.
Love it.
Next.
Unless it's lightweight concrete.
Yeah. Okay, so I just picked this off the web, and it basically covers the same thing that that Trevor covered. Next one. Set it up so that it's just one page on the slide. If you could. I'm glad he's doing this. I don't know how to do it. There we go. Score. Bingo. So in Oklahoma City, the Muskogee Bridge Company workers were all from Mexico and points further south. And they called cement and concrete cemento. If the INS green van showed up, they'd all say tacos. That was their bar. Yeah, Mike, we're still looking at dual pages here, kind of thing. Boom. That's what I get
Can you
for
just mime
heckling.
it?
Yes. So, sorry, Helen. I'm not sure what's going on. I'm doing the slideshow. I'm presenting as a slideshow. I'm not sure what you all are seeing because I'm seeing the full screen. What are you guys seeing as the screen?
Well, right now we're seeing us.
Yeah, there is no
we
presentation.
were seeing the next screen showing up on the side.
Okay. Is that any better?
Nope.
It looks like you're no longer sharing, Mike.
Right.
So we
Yeah.
may have to revert to whatever you were doing before. At least we were able to see the main screen.
Okay, sorry about that. Let me.
No problem.
Let's see.
It wouldn't be the BS and Beer Show if not for technical difficulties.
There
Maybe
you
this
go.
will work.
Perfect.
You did it,
Beautiful.
Mike. You're
I did it.
amazing.
All right.
Yeah,
Wild
really.
Nobody touch anything.
Thanks. Thanks, Mike.
Yeah,
Okay,
sorry about
so
that.
I mean, everybody out there that's not in the business talks about the cement slab, the cement beam. Well, and some of those people mix up beams and columns. But yeah, water and air, 20%, stone and sand, 70%. And this is, the stone and sand is where this mixture becomes inexpensive. It's also where it becomes local. The stone and sand, well, all right, unless you're in Oklahoma City, you have to get your aggregate from 2 states north. True fact. Cement reducers, one word that Trevor didn't use, pozzolans is one of the words that they use for the cement reducers. Cement with alkali will make what's called ASR, alkali silicate reaction. And it looks like this gold brownish rectangular veining. It means your concrete is going to die. And you know, the cement that we talk about as being cement is Portland cement. It's what everybody thinks of as cement. There are other cements. Go to the next slide, please.
Does that work?
Pretty
Not
please.
yet.
Give Helen the clicker.
Well, we were worried about Helen's connection, so we were going to have Mike do the screen sharing because he
But,
has
you
a
know,
more
I
solid
can-
connection.
Perfect.
I can try sharing. I ain't scared.
Yeah, that might be
That might be best. Yeah.
just because I seem to be having trouble with it.
All
So
right.
far- So
What
far,
are you
Helen, you're doing
seeing?
pretty good.
What are you seeing now?
A portion of your screen.
About 50% of it, the right side.
Crete. Lightweights.
All right. Stop
And we
share.
reverted to a very narrow line down the middle. And I
An
think the
eighth of your
miming was
screen.
really the way to go.
All right. What about this one?
We're getting closer. Yep.
Winner.
Okay. Well, you've still got the stuff on the side. We're just going to carry on because
Yeah,
that's
yeah.
fine.
Works
right.
for us.
Let's
Mhm.
go right down to here. Okay, so I wanted to talk a little bit about concrete testing. I went and thought about it, and I've probably done 75 to 100 concrete tests. First thing you do is check the temperature. So this screen on the left, the photo on the left, that's your thermometer. And then you've got the standard air test. Yeah, that's out of order. Okay, that didn't work. Okay, next is the slump test. So I've got a YouTube that you can watch if you want to, and let me just swing this right over into, there we go, enter. So I put that over in the chat. There's a completely different test for super plasticized concrete. Basically, it's a pretty inexpensive test. You need a reasonably clean sheet of plywood. You need a standard cone, which is 12 inches tall, and you need a rod. And some people say, oh, you can use rebar. This guy actually shows the right way to do the tests. There are some other YouTube videos done by people whose names I will not mention, who don't say the right thing about doing the test. If you're going to do the test, you might as well learn how to do it right, as opposed to guessing. So this is the answer. Super plasticized concrete, you go and dump a token, whatever the amount of concrete is, onto that, onto a flat plate, and you see how far it spreads out, and you measure the diameter of the puddle you get. Really cool. Never had to do it. Come on, machine. There we go. Okay, so somebody was asking, you know, how come the Roman concrete lasted so long? It didn't have rebar in it. Water loves to find rebar, and then bad things happen. But the rebar takes tension. The concrete, it can take this much tension, and then it dies. And so we have the concrete to form a matrix that holds the rebar, and the rebar acts as the tension strength. You're not going to have a concrete beam without rebar. You're not going to have a slab that you dump a whole lot of loads on without rebar. You're not going to have a slab that you drive a heavy truck over that doesn't have rebar. It also takes the temperature expansion and contraction. Every material expands and contracts with temperature. Most of them contract as it gets colder, and you know, most materials, not including water, of course gets bigger as it gets colder. It also takes shear loads, which is why engineers have so much fun detailing where the rebar goes. We use deformed bars because they hang on to the concrete better. They used to do square bars in like 1900. Round about 1920, they started twisting the square bars and found that that gripped even better. Round about 1930, 1940, they started coming out with the deformed bars that you and I would recognize on a job site. I like them tied every other intersection as a minimum. The rod busters at Chinbro were all taught by Harold Dooley. And Dooley taught 2 crews of rod busters how to tie rod using a reel and nips very fast. And it was the carpenters that were using the wires with the little loops and the yo-yo. And the reel and nips guys looked at the yo-yo guys and just, you know, dismissive sniff. They've now got a rebar tie gun, kabang, kabang, kabang. And it just means that you're going to get less carpal tunnel. Your rod installation crew will be more alive at the end of the day. Concrete also needs standees and concrete blocks to hold the rebar in the right place. And a standee, I went and was given some standees that were number 3 bar for the job site that's behind me right over here. It was a 3-foot deep slab, and they had number 3 standees. They're only 3/8 of an inch thick. And so I doubled them up and used them in a third of the area and told my rebar supplier that the next ones needed to be number 4s and I wanted a bunch more. I was a big client at the time. They were very friendly when I asked them for a little better support. Welded wire mesh, you only want to use flat sheets. It comes in rolls, but the rolls tend to not lie flat. So part of it will stick out of the concrete and part of it will be down on the soil. And if it decides to not stay where you've put it, it could rebound, bounce back, and people have lost their eyes. So I always specify flat sheets. It's just smart. And those want to be tied. You lap it over one cell and you tie every other cell. Fiber mesh is temperature steel only. It makes kind of a furry look to a slab. The fuzz will wear off and then you won't see it at all. It's good for some things, it's not good for others. And there are different kinds of fiber mesh. There are crinkly fiber meshes, there are smooth ones, but I only use it for temperature steel. Rebar, a number 4 is 4/8 of an inch in diameter, so that's a ½ inch. A number 8 is 8/8, so that's an inch. So good design, you want to have number 4s with number 6s on a job site, or, you know, on this one, number 9s with number 11s, so that people can easily see the size difference and they don't make little mistakes. They still made mistakes like putting the big mat on the bottom instead of the top, but we got that fixed on the QT. And then I just thought, you know, Travis is doing all this other stuff. I'll just do problems I've seen. So really big block of concrete, that 400 cubic yard block of concrete was the inertial mass for a roll grinder. It takes a paper machine roll and makes it perfect. And this was the inertia to hold that roll grinder so that it didn't shake itself to death. If it's too hot, you actually add ice in controlled amounts. You plan this out with the dispatcher well in advance. I have seen this used on really hot days. Ice is not my preferred method, but then again, I'm from Maine. Yeah, if there's not enough people to install the concrete, call it off, send the trucks home. I have one job site where the contractor did not have enough people and Helen picked up a trowel. I'm not the worst finisher I've ever seen, and we got it done. But that contractor is never going to work on any job of mine ever again. Creep. Yeah. Using a pump truck, plan on a 1 inch less slump at the nozzle. So you go up, you climb up on the truck and you look up in the top, up ahead of the chute. You can see the concrete as it's slumping over the veins inside that mixing tank. And I used to be able to look at it and say, that is a 3 inch slump runner. But if you run a 3 inch slump into a pump truck, it's going to come out 2 inches of slump on whatever distance far away that you're running it. And that's going to be consistent throughout the day. It's not just how much you're wetting the insides of the pump truck and the pump pipe. Okay, so the vibrator dies. Pull out the backup vibrator, which means that you should have a backup vibrator. Rotting or using a shovel, it just doesn't do as well as a vibrator does. And you can get a mix that's made so that you don't have to vibrate it. But those are expensive and they will cure at a different tempo than the concrete that you're used to. I had this once. The concrete mix is the wrong color. I asked the driver, I says, the cement added to this? Oh yeah. I says, run a little out in the chute and you look at it. It was the wrong color. It was brown. Don't put that in the forms. It didn't have concrete in it. I was so right. And I was just out of college and I was a sweet young thing. And I'm like, So then they believed me. That was nice. Form blowouts. Oh, every concrete placement, and engineers don't call it concrete pours or cement pours. We call it concrete placements. You place the concrete. Right. Form blowouts, avoid it, brace it, properly connect the forms, use all the form ties, have somebody check it. Ben is smirking. Ben, has this happened to you? Oh, good.
You're on mute again.
All right. The job site behind me, this one, was a reinforced concrete set of tanks for a wastewater treatment plant. We were placing a 2.5 foot thick wall, about 25 foot tall, about 30 foot wide, with a pump truck. The valve died. So Chinbro went and called up somebody at their job site in Boston, while somebody else called the valve replacement store. And the Boston people drove over to the valve replacement store, picked up the valve, and drove it all the way up to Winslow, which is a couple hours into the state of Maine. Meanwhile, we're going with vibrators, wheelbarrows, buckets, just trying to prevent a cold joint in the middle of this wall. Managed it. Oh my God, it was amazing. The inspector had a bad evening the night before. Guy I worked with in Oklahoma City, we were building the intersection of I-35 and I-40. Had 4 sets of bridges, 7 bridges total. And one day Phil went out the night before and he had a little too much to drink. And he came in, looked at me and said, "I'm sending that first truck back." Like, Phil, you can't do that. I mean, you have to look at it first. It has to actually have something wrong with it. Phil looks at me and he's like, "Nope, that first truck's going home." The first truck came, it was beautiful. It was lovely. Phil looks at me, climbs up into the cab of the truck. And the cab of the truck has a little counter that counts how many times the cylinder has rolled around on the mixer. And it should only say, 55 to 75. But, that's the distance that it goes from the plant to where you're going to drop it off. Most of the truck drivers ignore that. It said 55,000. And Phil sent it home. Oh my God. He just had a bad night the night before. Other things that I've seen, carpenters. You've got to watch carpenters every minute. They toss their pizza boxes in there. And, when I was 22, I climbed into the forms and took them out. Now I make them remove them themselves, lazy beasts. Okay, a bag of sugar in the truck, you confiscate it. Sugar extends how long the concrete will stay flexible. So if you've got your concrete and it's a little bit old, you put a little sugar in it. What it does to the strength characteristics, oh man, it creams it. Keep your sugar for your cookies. Retempering the concrete, if you've already placed 2 yards and it's been an hour, you might think you want to go and put in 6 more gallons of water into the mix. Don't retemper the mix. Get your concrete out of the truck. It's a good way to get a bad strength result, because what it does is it makes a mess of your water cement ratio. Lenton couplers figured into the job behind me. They needed to drive a crane over a spot where there were a whole bunch of standing rebar that were number 9s and number 11s. That's 1 1 1/8 and 1 3/8. So I said, and I was 22, this young thing, and it's like, oh my God, there's a girl engineer on the job site and everybody's getting all excited about it. So I walk into the trailer and Newton is sitting there with his feet on the table, and all of the other supervisors sitting there, and they're trying to figure out what they're going to do. Mrs. Watts wasn't Mrs. Watts then. I said, what about Lenton couplers? I made an order that day for $45,000 worth of Lenton couplers. God, it was fun. Super hard floors. are made much like super flat floors, and basically they beat the heck out of the paste and they run over them a bunch of times, and then they go and they cast some aggregate on the surface and beat that in. Kind of cool. Super hard and super flat floors are used in like big warehouse stores. You might find them in Home Depots, something like that. Putting the big mat of rebar on the wrong side of the concrete, the heavy mat of rebar goes on the tension side of the concrete. You've got two tension sides of the concrete, you got rebar on both sides. Welded wire mesh not ending up in the middle of the slab. It's really difficult to get it in the middle of the slab. And don't be thinking that you can put down all your concrete and then stomp it in. It won't go. Yeah, difficult. All right, it's concrete's job to shrink while it's curing. If you have big areas of concrete, either vertical or horizontal, you're going to need a joint. For slabs, the joint is 1/4 of the slab thickness. A 4-inch slab should have joints at 12 feet and no more than 15 feet apart. You can saw cut it within 8 hours, or you can go do something with a zip strip. I like the zip strip myself, but old concrete's problems, number one problem is cracking. The other number one problem is water getting to the rebar. All of the other problems comparatively are little problems. So when Trevor was talking about density and porosity, this is what's going on.
Hey, Helen, I'm sorry to interrupt, but we're running out of time, and I want to make
Okay.
sure that Chris gets a shot to get his slides up and we can get some questions in. So
All right,
if you want to just take another minute, if you want to hit some high points in the last couple slides.
this is, I went looking for concrete stuff for this presentation. This is the recipe for chocolate concrete. It's made in the schools in the UK, and it's everybody's favorite dessert. There you go. Good, I'm all set.
Dessert to finish it up. That's perfect. Thanks,
You're
Helen.
welcome.
So, Chris, you did have a few things to share, and then we'll kind of get into all the questions, because obviously Trevor's and Helen's presentations have already generated a ton of questions, and there's been some feedback in there already. But I believe you have a lot to offer, because one of the things that I saw leading up to this was a video of the product that you developed, and I'm hoping that you'll share a little bit about that, even if it's not in your presentation. But whatever you want to share, please begin.
Yeah, I will. Thanks, everybody. First of all, I'd like to thank everybody for actually using the word concrete and not cement or cinder block. It just makes me so happy to hear that. Or cement sidewalks. But, you know, not a lot of people know about concrete. So this is great that you're having this. What I'd like to do is just bring to the table, I think, what the industry is doing and the cement, what I do know about the cement industry. And I know they're trying desperately to address the carbon footprint of the material. And there's a lot of work going on behind the scenes that I don't know if everyone's really aware. There's a lot of stigma around concrete and that it is not, you know, favorable in green construction and all that, but it's essential. And I think everyone realizes that they need to use it in certain situations. And the industry's working very hard on it. I know Lafarge overseas is working on a low carbon cement, and as well as carbon cure. There's different things like that. But I can tell you what we're doing in the concrete block industry. Let me share, first of all, some images. See if I can do this right here. You got that? You see that all right?
Yep.
Okay. So here we have a regular concrete block. I mean, this is something we make, a lot of people make across the country. The benefit, at least of a concrete block, when you're looking at embodied energy, is at least it's already cored. So you already have much less volume of concrete relative to your wall size. So that's nice. So if you have a foundation, you can use blocks. It's quick to use poured concrete. It's more difficult to find people to put concrete blocks in for a foundation, but it does use less concrete, therefore less cement. Poured concrete is strong, but sometimes unnecessarily so. So you don't always need to have all that strength. You know, this might just do fine. This is what we've been making for about 100 years, and it really hasn't changed. In Europe, I went to a building show in Germany a couple years ago, and really, these are certain shapes that they make with concrete blocks. And these concrete blocks, these are sections, and in these concrete blocks, they put mineral wool insulation. So they're really thinking about everything they're putting into the blocks as well. This one looks like it's made with pumice or some sort of a volcanic material, which adds, it makes it lighter, a little more flexible. It adds insulation value to the product. And all these little things start to add up over time. They'll have, you know, offset webs to try to reduce the either the cold or the heat coming into the structure, make it more energy efficient. And it's lighter, easier to handle. Here's another one. This one is also probably made with pumice. I didn't really find any blocks over there that were made with actual solid concrete. It's not as common as here. So they really think about how they made blocks and what they put into it. Oh, I see, this is made with Leopor. Leopor is essentially what they do is they take clay, as far as I know. I looked into this as much as I could using Google Translate, but Leopor essentially is clay. They fire it and it's run in a tumbler, and it makes different size aggregate clay balls in which you can use however you want to make concrete products. So they have clay in the concrete block, and these also have air in them, so they have a little more insulation. This is a block common in southern Germany, and it's clay. And they extrude this product much like a brick. They have a die which creates all these little voids, which, you know, is like a beehive. It's like a honeycomb. So it tends to both absorb energy because of its density, but also help insulate. They throw in, as they mix the clay, they throw in sawdust. And then when they fire it in the kilns, the sawdust burns off and you're left with more air chambers in the actual block. They think a lot about this stuff. This is another one with mineral wool. Again, offset webs. All these blocks typically with this insulation, they run up to 500 millimeters, typically 400 to 500 millimeters, which is 16 to 20 inches, just about thick. So they have all these monolithic wall systems over there. Now they're beginning to do these cross webs where they're diamond, they're a little stronger, and they're really counting the energy efficiency. I believe they said it was something like 7 to 10% more energy efficient due to the configuration of the product. So, you know, as we look forward in designing concrete products, you know, how we take this concrete and how we organize it and orchestrate this wall really can be beneficial. It'll do anything we want to do when we put it in our machine. We just have to have the right mold. But a lot of technology and a lot of research has to be put into the development of these blocks to make better use of the concrete that we do put in it. This one has little styrofoam pieces that they put in. I believe they mix it with graphite. Perhaps you guys have seen the graphite-based EPS insulation. I believe it's supposed to be more energy efficient. They use it a lot over there. So my guess is it is. This is a larger block, and you can see the effort that they've taken in order to really make this so that it's more energy efficient and lighter. This is a typical construction, southern part of Germany. This block is almost a 20-inch wall, and they filled it, I believe, with perlite. Those are different images of European blocks. We have nothing like this here. This is similar to what we've worked on. And let me go back, sorry about that, to the beginning. Which leads it to this block, which we developed a few years back after I went to Germany. And it's a 16-inch thick unit, and it has offset webs, and it has EPS inserts in it that are custom to the cores in the block. On both the inside and the outside of the unit, there is a chamber that is designated for electrical use. The distance between here and the back of the wall here is 2¼ inches, which will accommodate a 2¼ inch electrical box. And then you're free to run electrical within the wall after it's constructed. This eliminates, if you want to use a block wall, often it's use a 2x4 or some sort of a strapping and then sheetrock in order to get the electrical in there. And we've essentially made it so that you can eliminate that and just put the electrical right in the wall, and then either plaster or stucco over the wall just to make it smooth with different effects. As far as what we do in making, you know, your standard concrete block and even the block, the comfort block unit here, we mine our own, we have our own sand and gravel pits. We mine those, we bring it to our facility. We crush it and we wash it, and we separate it so that all the particles are exactly the sizes that we want. So we have incredible control over what we put into the block, and that maximizes the efficiency of the cement. And when you do that, of course, you can reduce the amount of cement. We use a pozzolan, as Helen indicated. That pozzolan is a slag. We've had good use with slag. We replace up to 50% of the cement with a slag. So in taking the slag as a pozzolan and good aggregates, we're able to really reduce the cement overall considerably. It makes for a better block, actually. I mean, we do this. We've done this for quite a while, but it also has other benefits. Then it's also cured. The concrete is manufactured inside, as you can imagine. So we have incredible control over the amount of moisture that we can put in. We have microwave moisture probes in our aggregate bins so that we can dose the aggregate precisely by volume, so that it is always tied by volume to the cement. It's incredibly difficult to do when you have a ready mix situation. I know, because we had ready mix. So when you manufacture a concrete block or a paver or something in a factory setting, you are able to do all this, and you can run exactly the moisture you need in order to maximize the cement and activate the cement. You can put admixes in the concrete as well to basically excite the cement particles, so that those cement particles spread out and they reach and grab a hold of all the aggregate. So you're assured that whatever cement you do put in, most of it is being activated. There's a lot of cement that's not activated in concrete. A good admix and good mixing time, and I think Helen could probably attest to this, seeing this in the job, you have to mix it a certain amount. You have to make sure it's thoroughly mixed. You're going to get your maximum strength out of that, and you got to watch your temperature. We're able to cure our blocks in a controlled environment as well. That means we can put 95% humidity, 110-degree chamber, and the water will not leave the concrete. It stays there and does its job. If the water leaves the concrete too quickly, it reduces the strength. So, when you get a concrete block, typically, if the manufacturer knows what they're doing, and a lot of them are all set up the same way, you can be assured that it's always going to be the same or pretty close to it. It's a nice way. It's delivered to the job site. You're not worried about temperature fluctuations. So it's a really nice product. The only thing you have to worry about is the mortar at that point and the grout. And so that can be a little more problematic. with this particular product, the Comfort Block line anyway, we've gone to calibrating the block. Most of the block you see here in Germany have all been calibrated, and I'll find that picture right here. If you can see, there's a thin joint or relatively no joint. He's spreading mortar here, but they also use adhesive now. And in doing so, that mortar joint has been reduced. It's more energy efficient. Because when you have a mortar joint, it takes up 10 to 13% of your wall. And that can add up to a lot of cold joints. So all these things, I just want to let you know what we're doing, I guess, in the masonry world in order to make sure that concrete and cement is giving you a better value. It's giving you a lot of benefit to what you're doing to it. And hopefully the improvements that we've done and the improvements that are being done throughout the world with masonry offset what we're doing with the carbon, the embodied carbon energy. And also it'll last a long time if it's done as well. That helps, right? So that's really all I have to say, I guess. And I'll take questions, moving forward.
Thanks, Chris.
Yep.
I guess the first one, the immediate one that pops to mind is, what is the R value of your blocks?
R value is really tough. In masonry, it's because it's resistance value. But we've had some calculations done. The block we have, we estimated around an R30. And that's not a true R value, but it takes into account the thermal, the dynamic properties of concrete and how it retains and releases heat back into the structure. We've done some dynamic thermal modeling, computer modeling, and they give us the information back in kilowatt hours per square meter used per year. So that's how we have it. I don't have that number with me, but it's different. It's different according to the different zones you're in, climate zones. Down south, it's going to perform incredibly well. Up here, it's a little more difficult. It's pretty cold, but it still performs very well because of that. But it's an R30. Of course, you still have to practice all proper air sealing and all that kind of stuff, but it performs very well.
Thanks. One of the ones that we kept getting early on was about using crystalline waterproofing admixes like Zypex or things like that. What are some things to consider when using those kind of admixes?
I'm a fan of them. I mean, Zypex is essentially Portland cement that's been finely ground, and it kind of clogs up all those holes, makes it less porous. So, even if you use something like that, though, you might still have a large, like, open crack that can occur, and they're not necessarily guaranteed to clog up a crack like that. So you still need to use proper detailing and detailing of your joints and waterproofing membranes.
There were some other questions about the addition of fiber for placing slabs. One, you want to chime in and describe some of the benefits and drawbacks of using fiber and what happens there?
Well, I use it all the time on Kansas City projects and actually projects all over the place. We use a macro fiber as opposed to a micro fiber. The microfibers are the small, like, hairy ones that we've all seen. We never use those, but the macro fibers are larger, usually like a propylene material, and they'll make the surface of the concrete a little bit hairy, but they will rub off with just traffic. And you can also just take a torch to them and burn them off. But they are used, I don't use them structurally for flexure, but I use them to handle all my crack control on slab on grade and get rid of all the rebar, make it a lot easier to place concrete.
Is that only viable for flat work? You can't really use that. Columns and things like that need the steel, correct? Any slab in tension would need the steel still, or
Yeah,
no?
if you've got flexure in your member, you still need reinforcing bars. But for slab on grade, it's continuously supported, we would use it. I mean, I've heard of people, I think in Europe, of course, where they're always doing fun things, using it for flexure, but I don't know of any projects in the US that have done that.
There was another question about using, I'm trying to find it here, micro rebar or helix. That's a product I'm not familiar with, but it came up in the conversation.
I'm not familiar with it. I mean, there are steel versions of macro fiber, and that might be a version of it. I'm not sure.
Consolidating, how do we know when our concrete crews are consolidating properly? You know, are there some rules of thumb for, you know, size of wall or duration of pour? Or
Helen, you want to?
Um, yeah. I know pretty well if they're not consolidating properly. You know, if you've got a big concrete placement, the concrete goes in, somebody's there with the vibrator, and then the chute moves over, and somebody's there with a vibrator. If the vibrator hasn't hit it, you're going to end up with some rocks here and some paste over there, but they're not going to be bound together. It's not going to be uniform. And then you're going to get things like bug holes and cold joints and messes.
Yeah.
You can go and install concrete with a super plasticizer, and they do make an admixture that you do not need to vibrate the concrete with. I've never used it.
that's self-consolidating concrete?
Right.
Yeah, self-consolidating concrete. And I mean, I'm sure it's a lovely thing, but whenever you add those admixtures, something else will change, you know, and some of the other characteristics of the concrete will change. So if you're going to go and do one of those mixes, you go and ask them, how is this going to change? Am I not going to be able to take 2 hours to put in 8 yards of concrete? Do I have to get all of the mud in the right place in 30 minutes? Okay, then I need 10 more people. And not the kind with their fingers on their cell phones. I mean, they're all going to have to be active people with boots and shovels and vibrators.
In Kansas City, at least the commercial ready mix suppliers are experts in all of that. And you could call them up and they could,
Yep.
They've got 1,000 different mixes for every sort of application that you might want to use.
And you want their standard mix. Don't have your engineer go and say, well, I want this and that and the other. I want a standard mix for X thousand PSI concrete at 56 days or 28 days. Never had anybody say 78 days, but my day will come.
With you saying that, Helen, so and Trevor, you showed that you guys write your standards based at 56 days, but most of the industry goes off of 28 days.
Right.
Why is that? I know you alluded to a
Voodoo
little bit
number.
of that. Voodoo number. That's
Voodoo
what
number.
I thought. No.
Somebody picked that number off the
Kind of
shelf
arbitrary.
and said, yeah, this is going to be the number.
Yeah.
And it's become the number. And you know, most of the strength in the concrete happens in the first 24 hours. After that, most of the strength in the concrete is going to happen in 4 days. So we'll go and we'll test our first cylinder at 7 days. Is it fine? Great, off we go. But concrete will gain strength quickly at the start of its life when it starts to cure. And then it will keep gaining strength. It will keep hydrating. The water will keep mixing with the cement for the rest of its life, which is neat.
Yeah, Helen, you said something that rebar, the lack of rebar is why Roman concrete has lasted so long. And so when should we be using things like epoxy coated or fiberglass or stainless rebar?
I don't know about you, Trevor, but my book is really mixed on epoxy rebar. When epoxy rebar rusts, it looks just fine and you poke it and there's nothing there but the epoxy.
Yeah.
And some rust.
Yeah,
I mean,
we're not huge fans of epoxy coated rebar because it gets holidays, it gets a little nicks in the epoxy coating, and then like I forget the chemistry that's going on there, but it kind of concentrates at that particular spot where the holiday is, and the bar will just rust all the way through at that one spot, and it'll be perfectly fine everywhere else. But a bar that's rusted through in
electrical.
one spot is useless, right?
It's electrical. It kind of makes
Yeah.
a battery.
Right.
And because there isn't any other steel handy but that one spot, all the energy goes to that
Yeah.
spot.
That's right.
But and as soon as it rusts, the iron molecule is this big, and the iron oxide rust molecule is 4 times as big. You get enough of those rust molecules and you don't have enough air holes, it's going to go boom and snick and bang and crack.
But Ben, I mean, I think there is some interesting development going on in some of these higher strength rebars at like 80 KSI and now 100 KSI have they're more like a stainless. I think the 100 KSI bar is. So there's not a lot of information, like there's not a lot of availability, and it's expensive, but I'm interested to see what comes of that.
But they have found that those extra high strength bars don't hang on to the concrete quite as well. And
well, yeah,
they really got to work together.
You got to have longer lap splices. Yeah.
Yeah.
Right.
I see there was a couple people that were asking about basalt rebar and fiberglass rebar. Have either of you had any experience using that at all? I know we brought some in, we sell some. We just started fiberglass rebar. And it's interesting because I looked into it a little bit. I said, why can't we just replace steel, right? Because around here in Maine, near the coast, there's seawalls, and you have a lot of ocean exposure, and salt really gets into the concrete, and it finds that rebar, and then see you later. So a fiberglass or a basalt rebar does really well in that situation, and maybe on slabs where it's exposed and where and they're using it in bridges. I believe Helen, they use it in a bridge, I think going to Kittery. I believe they did.
They use it primarily, and the epoxy rebar they use primarily in the top layers. So you've got a road and it's going to be, or a bridge deck, and it's going to be this thick. You'll have one layer at the top and one layer at the bottom. Well, the bottom layer might be regular rebar and the top layer might be epoxy. And we did some of that in Oklahoma City.
Okay, so I believe, and you can check on this, that they used a fiberglass rebar in the bridge, obviously to prevent the corrosion and the interaction. The downside of that basalt and fiberglass is it doesn't really bend. It will bend to a degree, then it will break. So in a seismic application, what I believe is that the steel rebar tends to bend, and so it'll keep going and keep moving, where the fiberglass might hold better and then suddenly fail.
Yeah, we have the same issue with carbon fiber, and that's why we see very little use of that.
Okay.
High strength, but then it just fails. And as engineers, we want ductility in our structure so that we see the failure happening before it kills someone. Right.
Great. That's a good idea.
Are any of you familiar? Are any of you familiar? There's a GBA article that was coincidentally posted just this week. 3 engineers at the University of Michigan are working on a bendable concrete, and it's modeled after the nacre, I think is how you say it. It's the material on the inside of abalone shells, that iridescent material. And it's strong, flexible, and bendable. Are you familiar with this product that they're exploring?
Not at all.
No?
Nope.
Okay.
Nope.
Well, I shared the link. I can't say much more about it, but I just was curious to know if it was on your radar. It's an interesting article. It is sort of, the whole point is to sort of get away from the brittle nature of concrete and find a solution for making it bendable. So anyway.
I worked on the concrete canoe race for
Yeah.
2 years in college.
They were popular in Rolla also.
Yep.
Nice.
Yeah.
Yep. Great excuse for beer and beans.
I think the
Maybe.
most interesting tech that's starting to hit the market is nanosilica, which is very
Mm.
tiny silica particles. I love it because it helps the cement reach a much higher hydration, so you can use less cement, and it kind of plugs up all the pores, so it makes for a much more durable concrete. In my opinion, if we're gonna go through all the carbon costs of building concrete buildings, I want them to last forever, you know, and so durability is a big important thing for me.
We had this one pop up a couple of times so far. What do you guys consider to be the most sustainable concrete mix for, you know, obviously typical residential projects, likely from a carbon standpoint? Or how do we tackle carbon most effectively?
The one that lasts the longest.
Oh,
The first
and it's also, you want, every material needs to be used well. If you're going to use water, use it well. If you're going to use solar panels, use them well. Don't put them on the north side if you're not in Australia. If you're going to use concrete, don't use it to make concrete countertops. That's just dumb. And
Careful, Helen.
heavy.
So I guess, Trevor, you made a comment earlier that the long-term killer of concrete is the permeability of it. So just because I've been reading a little bit about it recently, like products like Zypex and these microcrystalline crystalline promoters can also act to reduce permeability of the concrete. So maybe is it a smart idea to add those to the mix, even if we're not using them as a means of waterproofing, because it's going to decrease permeability?
Yeah, I'm a fan of them, and there's also a mix. It's I just forgot the name of it, but it's a moisture vapor reducing admixture. It basically takes the free water in the concrete and turns it to a gel, so it can't get out of the concrete. It plugs up all the holes. Yeah, I'm a big fan of those. I think those particular types of admixtures will help with the long-term durability. But also, if you think about all the concrete on your building, a lot of it is like a basement slab. That's doesn't need to have that in it. It's not exposed to freeze thaw or weather. But your foundation wall might be, so that you might want to consider it there, or your slab on grade outside. So let's think about, these are expensive admixtures. Let's think about what element we're using them in and use the appropriate thing.
And, one of the things when we talk about these cement replacers, slag, fly ash, silica fume, these are all waste products that go in a dump.
Yeah.
This is a much better use for them. And fly ash, don't use it for large slabs, because there are small amounts of chemicals that are going to make the slab not cure in a uniform fashion. So you might think you'd be getting on it with your blades, in 4 hours, and they show up and it's already too hard, or it's too soft and you have to wait another 4 hours. So the fly ash, I just tell people not in flat work, not in a slab.
Yeah, we limit ours in slabs, but we use a lot of it in footings and walls because it doesn't really matter there. And fly ash, it delays the set of the concrete, but it slows that curve that concrete will cure and harden at over time. And that actually creates a denser and lower porosity, a more durable concrete. So, and it's cheaper.
Right.
I mean, at least it was.
And so you ask for the concrete plant's standard design that has 40 or 50% cement replacement, and you tell them what you're going to place, and they're going to go and look at all of their piles and say, the best mix we can make for this guy's project at the best cost is going to be this one right here. And so we're untying the hands of the concrete mix plant people and letting them go and make the best thing that they can make out of a very variable product. I mean, you know, you go and take a tree and turn it into paper. You're taking something that is extremely variable and turning it into something that's absolutely uniform. Well, we're asking the concrete plant guy to take rock out of this pile here and sand out of that pile here and cement out of Dragon as opposed to somebody else and turn it into something that works.
I interestingly just had pushback today about using fly ash and slag as an admix to reduce Portland over the issue of it leaching into groundwater, and essentially we're spreading heavy metals and stuff like that.
Like
I
through
don't-
the
I don't
concrete
know of any
mix?
evidence of that, but I don't.
Yeah, I'm not
Yeah.
familiar.
Sounds
with
like
that.
a reach.
That was my thought, but it's just it interestingly came up in conversation today when we're talking about mixes.
I guess if I were to pick one, I would be most concerned about fly ash due to its nature of where it comes from. Slag is pretty consistent, very consistent, which is why we use it. Not convinced fly ash would leach in, but I don't know that.
Yeah.
We're kind of nearing the end of our time tonight, and I want to make sure everyone has an opportunity to kind of get their last word in. I feel like we didn't get to talk much about block, which I think is a really great way to utilize concrete without waste and to be efficient with it and to introduce additional R value. So I'm suspicious that we may have to revisit this topic again. But since we're wrapping up, please take a moment for each of you to just sort of have your parting thoughts, anything that you want to leave our viewers with. And of course, have my thanks for joining us tonight. Very much appreciate it.
Okay. Yeah, I guess I'll just leave off. I wanted to mention the sustainability portion, and I think it's I don't remember if it was, I think it was Trevor that indicated, just don't have as little waste as possible. I know in using concrete masonry units, and if you design with them, they're relatively small, relatively speaking to the structure you're using, and really, if you plan it properly, there shouldn't be much waste, which is nice. You utilize the concrete as much as you can, and you don't throw it away. There is more information on our website at genestconcrete.com, and there's more information on the Comfort Block website, comfortblock.com. And feel free to follow Comfort Block or Genest on LinkedIn or whatever. Instagram, all that kind of stuff, and you can look me up too on LinkedIn, and I will track jobs and show you what we've been doing, for right or wrong. That I'll do that, and it's just it's information anyway. That's my spiel.
That's great.
Nicely done.
Yeah, I appreciate it, Christopher. I'm gonna look into your stuff more. I'm really interested in what you guys are doing and what you showcased in Europe. That's pretty wild. So
It's cool stuff.
yeah, cool stuff. Okay, I guess I've already talked a lot, so I don't have a whole lot more to say, I feel like, but I think in the end, doing it well is probably the most important thing. Let's build buildings that last. You can have a great mix that is super low carbon, but if we're bulldozing the building in 10 years, it's kind of useless. So that's all I got to say. So thanks for the invite. I appreciate it, guys.
I'm going to say every concrete placement is a heart attack, whether you have all of those things that happened that I discussed for, all of the years that I've done concrete. Every concrete placement is a heart attack, and you can either go in and be real smooth and do everything the way it needs to be done, and any surprises you're ready for, or you can get caught and then you have a jackhammer, and that's really bad. And Trevor's talking about durability, and you've immediately lost your carbon footprint. And every material used needs to be used well.
Great.
Thanks for having me.
Well said, all of you. I think that does it for us tonight. Kylie, Ben, any parting words before we say goodnight?
No, I think you've given people a lot to think about, and there were many questions that weren't answered. So, maybe another show is warranted.
It's a
So
daunting subject.
It is a daunting subject. It's
go and make that
just touched the
concrete cement,
surface.
that chocolate
speak.
cement. I want to know. I want to know how that comes out. I haven't tried it.
Everyone off to the kitchen. You got your homework. We'll see you next week. Thanks again.
Thanks,
Thank you
everybody.
all. It was a pleasure.
Good night.
Good night.